Okay. Hello, everyone. Welcome to Probably Approximately Correct Learners, the new podcast from your let all besties. I'm speaking the language of the youths these days. This is our third podcast, and we're excited to be joined by an awesome guest. And before we start our conversation, please like and subscribe to our podcast through Spotify, Apple Podcasts, or wherever you get your podcasts from. I see Sam laughing over here. I've become one with the youth, Sam, as you can see.
Yeah,
Um,
great.
we're joined today by my MIT colleague, Sam Hopkins. Sam is a theoretical computer scientist and an assistant professor at MIT in the Theory of Computing group in the Department of Electrical Engineering and Computer Science, where he holds the Jamieson Career Development Chair. His interests include, and I'm listing things verbatim from his websites, algorithms, theory of machine learning, semi-definite programming, sum of square methods, and bicycles. Before MIT, he was a Miller Fellow in the Theory of Computing group at UC Berkeley, hosted by Prasad, Raghavendra, and Luca Trevisan. And before that, he got his PhD at Cornell, advised by David Steurer. Sam, welcome.
Thank you. It's a pleasure to be here.
Good. So, just a reminder for everyone that listens, these conversations are going to be split into two parts at a high level. In the first part of the conversation, we're going to talk about research topics, and then we're going to shift to more beyond research topics. So, with that, let's take it away. So, Sam, what is the latest, research idea, project, work, or maybe like series of works that you have been excited about?
Yeah, sure. So broadly, I work a lot on algorithms problems that arise in statistics, especially high dimensional statistics, where we often see algorithmic challenges that go hand in hand with data challenges. So like sometimes your roadblock to making a useful statistical inference is that you don't have enough data, but sometimes you have lots of data and the roadblock is you don't have enough computation. So I try to understand when we can use better algorithms to enable statistical inferences that aren't possible without algorithmic improvements. So one series of works that I've been kind of proud of over the last, say, 4 years has been about doing basic statistical inference tasks subject to a constraint called differential privacy. So privacy means that you imagine that you're processing some sensitive data set. You're interested in doing statistics on some sensitive data set, like imagine that a data set contains medical records of individuals or location information from their phones or internet browsing histories or whatever it is that you wouldn't be appropriate to release publicly. But you want to draw some useful statistical inferences from that data set, right? Maybe your example that I like is you're like doing some kind of biological or health research, and you're using genomic information or health data about patients, which can't be released publicly, but you'd still like to publish your scientific findings that you drew using that protected private data. Okay, so this is a problem that's been studied for a long time by statisticians for decades. But in the early 2000s, computer scientists actually coming out of the cryptography community put a computer science spin on this problem and invented a definition called differential privacy. And in differential privacy is the mathematical specification for what it means for an algorithm that processes a data set to protect the privacy of the individuals in that data set. And basically, it means that if you are an outside observer who only sees the output of the algorithm, that you can't distinguish any non-trivial information about any one individual in the data set. Like the way it's usually formulated is that you can't tell if any particular individual was or was not present in the data set. So this can be formulated mathematically, and people studied for 20 years almost how you can design useful algorithms that have this privacy property. And the property has appealing, rigorous guarantees, so appealing that it gets used in industry by Google and Apple and Microsoft and LinkedIn and lots of big tech companies. And also the US Census has adopted it as its its own definition of protecting the privacy of individuals represented in the census. So this is like a widely used definition. Okay, so is this the level of detail that you want for like background here?
Yeah,
Is this fine?
that is great.
Okay,
Maybe let me just intervene 1 second and
sure.
ask. You mentioned in the beginning of your introduction, about basic inference tasks. What are some inference tasks that
Sure,
you can
sure,
you
sure,
can
sure.
actually perform with differential privacy?
Sure. So I think when I talk about inference tasks, okay, you these days you can perform a lot of things subject to differential privacy. Maybe it's good to draw a distinction between um, things that people actually do with real data sets in practice and
Mm-hmm.
inference tasks that we study as a little bit more toy mathematical problems that are simplified tasks so that we can study, that we can get really clean theory and clean and understandable theory about. And this is not a black and white distinction. There's a whole spectrum. But starting on the practice end, there are like prediction tasks, labeling tasks, like I give you some information about a patient and I want to infer whether a drug is going to perform well for them, right? That would be a statistical prediction task that I might use using a data set of observations I made about patients in the past and what a drug did for those patients. I might want to label images. That's a classic machine learning task. That's a statistical inference task. That's something we often do with big fancy deep neural networks. I might want to do some kind of unsupervised learning, like take a data set and cluster it into meaningful clusters that we sort of often, broadly speaking, I'll consider that inference. Tasks like recommending movies, recommender systems, this is inference. So those are sort of tasks that people actually might want to do. On the more simplified theoretical end, we often think about really basic statistics problems, things you might have seen in a Stat 101 class, like
Hmm.
estimate the mean of a population of individuals. I give you samples from a population, like imagine that they are the heights of people drawn from, I don't know, the Cambridge area, and you want to estimate the average height of residents of Cambridge. I don't know why exactly you'd want to do that, but this is a very mathematically simple task, right? I'm giving you a list of numbers. Those numbers are representative samples from a population, and you want to know something about that population. Okay,
I see.
so tasks away on the simplistic end are very interesting to study from a theoretical standpoint. And we have 100 years of statistics history that teaches us that if you understand the basic tasks well, you can design useful algorithms for the actual practically useful tasks.
Good. Coming as an outsider from this area, why is it so hard? Can you give me like an easy kind of like easily digestible reason as to why can't we just use our well-known and celebrated statistical methods from Stat 101
Mm-hmm.
um, to, just like do something easy and then just achieve privacy? Why is it such a hard task?
Yeah, it's a good question. I think a good way to, okay, there's maybe an empirical argument, and then we can try to understand what's going on underneath. The empirical argument, by empirical I mean scary things that we observe people doing, is that it turns out that I don't want to call such people hackers, but like you you can, using publicly released, statistically aggregated, supposedly anonymized information, draw shockingly detailed inferences about people in underlying data sets. So,
Oh, wow.
right, privacy breaks occur all over the place, and you can Google these things and read about them. And there'll be things that really actually maybe on occasion people see actual hacks, but more likely it's some researcher who exhibits that somebody could have done some private, what are these things called? Membership inference attacks is the like
Hmm.
jargon name for these things. But basically, this means taking publicly available data, and this usually means not whole data sets, but like things that supposedly have been anonymized, statistically summarized, et cetera, and somehow managing to extract shockingly private information like a list of people's addresses, phone numbers, work histories, stuff that you
Oh,
clearly don't
wow.
expect to be public. So the reason that these things are often published by researchers and we don't see the scary ones is because, of course, there's no incentive for people who have done this in a malicious way to show us that they've done it. But researchers can do this kind of stuff. So
Wow.
so that's scary. Now, why does that work? It's just very unintuitive that you can put together information from multiple different sources that is often publicly available on the web any one of those sources might look innocuous, but by cross-referencing different databases against each other, this statistical summary of a database against this one, you can make shockingly detailed inferences about what was in a database. I mean, there are classic examples that don't have at my fingertips, unfortunately. But it's not hard if you want to get a real feel for this to go. You can Google stuff about like membership inference to see examples of very unintuitive conclusions that you can draw if you have access to just a few publicly available data sets.
Yeah,
so
100%. I mean, we can also link some
yeah,
under the
we could
podcast
link some
description
resources
later.
Yeah, sure. So now maybe I can tell you maybe a little bit more mathematical version of what's going on. So the differential privacy mathematical definition is a really it's sort of intensely strong in the following way. It allows the adversary who's observing the output of this algorithm that I want to be private to know a lot of side information. Okay, and the reason to do this is because we want to think about observers, attackers, who have access to lots of databases that they might just get on the web because of some, whatever leak or, the yellow pages, whatever it is they have access to. And so the way this is modeled is the following. If I want to worry about privacy with respect to you, Chara, so there's some data set, it's a medical data set, okay, and I'm the attacker, and I am reading a paper that was published using statistics that were performed using this data set. And I want to know, was Chara in the data set? Okay, in fact, I want to know more than that. I want to know some private sensitive medical information about Chara. I want to know whether you express a certain gene or not, right? Whether you possess a certain gene. Okay, and the way the privacy definition works is it says, let's assume that Sam is really powerful and Sam actually knows everybody in the data set except for Chara. Okay, he knows who they are, he knows all their medical information. So he knows the whole data set except for Chara's information, and he sees the paper that was published. And then what we require is that I, Sam, not be able to infer anything about your sensitive medical information, even with all of this additional side knowledge. Okay, and that's what makes this really stringent. So imagine now a really basic task, like let's go with this height estimation thing. Okay, I know I'm switching around between medical and height, but we have this height example floating around. So what would how would the example go? I'm trying to estimate the height of people in Cambridge. Let's say that I know that I drew a random data set of 100 people, and I, Sam, the attacker, get to see the heights of 99 people. Okay, and now if I get to see the heights of 99 people, and I get to see a published statistic about the data set, namely the average height of all 100 people, I can do a little bit of algebra, and I know the height of the last person in the data set. Okay, so the Stat 101 thing, which is just take your data set and output the average, doesn't protect privacy of that last person in the data set with respect to an attacker who gets to see a lot of side information.
Got it. So you're taking like the hardness, I guess, is like this like worst case adversary that you're thinking about. This like omnipotent in some sense, like adversary.
Yeah, in some sense, the only thing the adversary doesn't know is the thing that the adversary is trying to infer. But they know all the side information that they want. Okay, and so it's a really strong adversary, right? It's a really strong notion of privacy. And there's a lot of debate about whether this notion of privacy is too strong. Like, do you really need such a strong mathematical definition? Are there really attackers who know everything? I think jury's a bit out on this debate, although I think people have very passionate feelings about it. And well, the argument in favor of the definition is that this definition allows rigorous guarantees, allows you to prove stuff about what the adversary can infer. It also, if you're uncertain about what adversaries you're facing, right? You're uncertain about what information your adversary has, what leaked databases they might or might not have access to. This gives you privacy even in the face of uncertainty about what your adversary does or does not have access to. So it's a very appealing notion. The downside would be, what if it's so so stringent that we can't actually design algorithms that achieve this notion of privacy. That would be problematic. It would then be sort of an empty definition. Go ahead.
No. So that's fascinating. I just wanted to ask, based on this definition, like what is the new spin that your work adds? Or I guess, is there any more specific setting within the the inference under differential privacy constraints that you're particularly excited about?
Yeah, so great question. So I have been working on algorithms which try to optimize the quantitative trade-off between the degree of privacy that they exhibit. So I should say that when you write down a mathematical definition of privacy, it comes with a quantitative parameter. It's called privacy loss. And this is some way to quantify how private an algorithm is. And if you ask for an algorithm to be perfectly private so that an observer can't infer anything about the individual that they want to learn about, it turns out you can show that such an algorithm can't be useful. It basically has to output just totally random noise. It can't output any interesting, useful information about your database. So you actually get a trade-off between degree of privacy and degree of accuracy. And I've focused on optimizing this trade-off quantitatively, because to get useful private algorithms, you want the best possible accuracy subject to some level of privacy, or vice versa. Now, let me try, and of course, people have tried to optimize this trade-off for the last 20 years. Let me put the spin on it. So for the first 15 or so years of differentially private algorithm design, people focused on designing algorithms which had worst case privacy guarantees, like the kind I'm describing, and also what I would call worst case accuracy guarantees. So what they would ask for, the way that they would measure the usefulness of their algorithm, is they would say, let's take the mean, the height thing for example. They would measure the accuracy of their algorithm by saying, if I look at the worst case over all possible subsets of 100 individuals in Cambridge, okay, it's data sets, and I look at the actual mean of that subset, right, the sample mean of that subset, and I compare it to the output of my private algorithm, how far apart are those numbers? Okay, so they're measuring their accuracy with respect to the sample average of the worst possible set of samples. Okay. But we don't really care for statistics purposes about the worst possible set of samples. We care about the set of samples you're actually likely to get. We care about random sets of samples. And so it turns out, it's shocking, but it turns out to make a huge difference in what kind of algorithms have good guarantees. If instead I ask for accuracy measured with respect to the sample mean for a random subset, which is the same thing as asking for accuracy with respect to the population average. So what it means is, suppose I accidentally go to high school basketball practice and I draw my sample from there, right? I didn't know I was doing that. I screwed up. I went to like basketball practice and I got like really tall people, right? I got this very biased, weird looking sample. I still have to be private. I still have to protect the privacy of the individuals in my data set, but I'm allowed to output a number that's very far from the sample average of the people in that data set, because that's a weird that's a weird set of samples. Okay, and I'm not penalized for that in terms of accuracy. So over the first 15 years of private algorithm design, people developed this kind of paradigm where what you do is you compute the statistic that you were interested in, like the sample mean, and then you add a little bit of noise to that statistic, and they showed, like, you add some random noise, and people analyze the heck out of algorithms like that. They work, they have the privacy guarantee, and if you measure accuracy in the worst case sense, the old way, those kind of algorithms tend to exhibit optimal privacy accuracy trade-offs with respect to that worst case notion of accuracy. But if you change the accuracy measure to the one that I would argue we really care about, which is accuracy with respect to an underlying population rather than with respect to any particular set of samples, it turns out that simple kind of algorithm, your just add noise kind of algorithm, usually is no longer exhibiting an optimal privacy accuracy guarantee. You can beat those algorithms. And so what I've worked on a lot in the last 5 years is designing new algorithms that are more sophisticated, that exploit the newfound freedom to not be accurate on weird sets of samples to get better privacy accuracy trade-off.
That is fascinating, and I imagine that these algorithms must also perform better in practice, right? Because as you mentioned earlier, like the world is not always like a worst case situation.
That's the hope. I think that we are getting there slowly. Practice if DP is challenging it for lots of reasons. It's hard to figure out what data set. Okay, first of all, if you like, when we do theory, we make all these assumptions like Gaussian distributions and blah, blah, blah that aren't, really totally reasonable in real life.
Mm-hmm.
If you go set up synthetic data sets that really reflect the assumptions of your theory, then of course, yes, you can show that the new algorithms do better. But that's not real practice. Real practice involves constructing algorithms that are robust to changing out underlying distributional assumptions, that deal with outliers. So we're not there yet in terms of robustifying and making really practicable this new generation of algorithms. Another issue is that in high dimensions, when we're doing high dimensional statistics, not like this population mean is a really low dimensional setting, but when we do sort of modern high dimensional stuff, image classification or something fancy, these newfangled algorithms, they're very slow. They're like impractically slow.
I see.
A big part of my work was to get those algorithms to go from exponential time, which is really completely hopeless, to polynomial time. So that's actually maybe the thing I'm most known for in this privacy community is algorithms for high dimensional statistical inference that get good privacy accuracy trade-offs and run in polynomial time. But the polynomial runtimes, they're pretty bad. They're pretty slow right now, just because these things are coming within the last few years. So we're still working on trying to glean insights, take what insights we can from the new algorithms that are polynomial time, but kind of impractically slow, and design actual runnable algorithms with code. And we have one work in that direction and some stuff ongoing. But I hope that over the next maybe 5 years, we can push these things towards practice.
So this is super interesting because you're touching upon a topic that is very important for many, many people that work in theory, like practice-driven theory. Sometimes, most of the times, our assumptions are very far away from what happens in reality. And when it comes to like a topic as important as differential privacy, especially given the applications that you mentioned with the census, with all these companies implementing differentially private algorithms, we may want to be more practicable compared to what we have learned to be as theoreticians. So I was wondering, how do you think about that? I don't like trade-off, and have you tried to reconcile it at all? Do you talk to people that try to apply these algorithms and try to, listen to their concerns, and then you adapt your theoretical approaches? Just a very open-ended question about how you think about this, like trade-off between practice and theory in this area.
Yeah, it's a super good question. And I'm not sure. I mean, it's hard. And it's kind of early days of this for me. Like I really was trained as a core bread and butter theoretical computer scientist, not even like a machine learner, really core TCS algorithms. And so this is sort of new territory for me within the last few years. So I'm really not yet good at it. I'm trying to learn, but I can say what kind of stuff I have done and how I try to think about it. So one thing is I have tried a little to speak to people who actually use these algorithms, who use differentially private algorithms. Like I haven't done a great job of actually seeking them out, but sometimes I'm at workshops where such people are. So like I've spoken to folks coming from the census. I've spoken to folks within some big tech companies that run differentially private algorithms. My experience so far is that I think this is something lots of people say, practice is idiosyncratic. Right? Like every time you ask somebody details of their particular implementation of DP, you'll get like a 30-minute discussion of a whole bunch of weird idiosyncrasies of the particular setting that they were running something in. And you don't want to like overfit to some particular idiosyncratic setting. So a lot of the conversation is going back and forth and trying to understand what is just one improvement to some basic primitive that which could be made, which might have an impact for them.
Mm-hmm.
So I'm not, maybe I should try to get my hands dirtier and really pay attention for a whole 30 minutes of details, but I'm not any good at it. So one thing I've learned is try to do things that you're good at, and I promise you I'm not good at that. Another thing though is, and this is something I've learned, I mean, I knew it, but I've really internalized it by bringing in students that are good at working with data, is that data sets keep you honest. So for almost the first time, I think maybe only the second time, I have a paper in iClair this year that has like actual data sets and actual experiments that we ran code on.
Congratulations.
Yeah, I know. I had a couple other papers with some code, but it was kind of a bit fishy data. This was real stuff. And it's great. You have this really nice loop of assumption checking on your data sets. And yeah, of course, if you only work with 5 data sets and you pulled them from some other machine learning paper, of course, just checking your assumptions on those data sets isn't that robust, but it's more robust than nothing. So I feel good about that. The trade-off is that the amount of human effort involved in doing stuff with experiments is very high. So yeah, you gotta lower your expectations on exactly how much work corresponds to one line of paper, but fine, that's life. What else? Oh, another thing I guess is sort of trying to take something that seems to be working reasonably well is trying to take small bites. So just because in theory we have this nice differential privacy definition and we have algorithms that end to end have the DP guarantee, I don't think that you have to try and translate the theory directly one-to-one to practice, right? I don't think that you have to say, okay, in order to do privacy research in practice, what I must do is construct an algorithm that has an end-to-end privacy guarantee and measure its accuracy and performance in exactly the same way that I did in the theory papers. I don't think that's how it works. There shouldn't be one-to-one correspondence between theory and practice. If you have one-to-one correspondence, you're doing both of them wrong, right? What you do is you learn a way of thinking about privacy from the theory, and you apply that as you're working on the practice. So to be clear, I still want at the end of the day to have algorithms that run in real life with end-to-end privacy guarantees. But I think that it's actually too much to ask for that right now. Like those algorithms aren't ready for prime time, and you'll just end up with a confusing mess on your hands if you go try to build something you're not ready to build. And so what I'm trying to do instead is say, okay, the theory tells us that this little component is going to be important, right? One component would be, it turns out, algorithms which let you take a trained model, like a linear regression or a logistic regression, and really fast figure out how that model would have looked different if one of the data points had been missing. What would the learned weights be if Chara's sample hadn't been in the training set? But I want to figure that out without doing a full retrain of the model. I want to run much faster than that. So we know from the theory that algorithms that can do that are a key component of private algorithms. And that's already on its own a pretty interesting algorithmic problem. Can you predict what happens when you drop a few samples from a data set without, can you do it really fast without retraining? Okay, so we said, look, let's just take that component and let's figure out how to do that in practice. And we're pretty sure, because we did all the theory, we're pretty sure that if we can do that in practice, it's a useful step towards good DP algorithms. So I think the philosophy here is breaking things down into really small parts so that you can optimize each part and you can understand, like, where's there room for improvement, where is there not, where, if you look at my opinion on the DP practice literature today is the algorithms are so complicated that you can't tell where there's room for improvement and where there's not.
Yep.
That makes it really hard to make progress.
Yep. I see. And I really, really like your insight about how your philosophy is about, like doing practically motivated theoretical research about, that you need to have insights from theory that you then want to apply in practice and break them down into like separate chunks. And I know that I'm not doing justice to how well you explained it earlier. But I'm really curious now, like, you mentioned earlier, and you mentioned this like a couple of times already. Um, this is not how you were trained as a PhD.
Mm,
And so I'm wondering, so two questions that I guess are like interconnected. One is, what was your path that led you to think about differential privacy?
hmm.
And how does your prior research experience and your training, because again, you also mentioned that you wouldn't even be considered like a machine learner in some sense.
Yeah, yeah,
So how does your past training inform the way that you approach research in this area right now?
great. Yeah, research is a random walk. So I can tell you what the preceding step in the random walk was for me.
Mm-hmm.
Um, there was, still is ongoing, a tremendous amount of work in the theoretical computer science community on algorithmic robust statistics, starting in around 16, so when I was doing my PhD. And I started
Mm-hmm.
working on this towards the end of my PhD in about 2017 or 18. I started working with Jerry Lee, who's now in the faculty at University of Washington on these things. And okay, so what's robust statistics? In robust statistics, the goal is still to do statistical inference, but with potentially poisoned data. So we're not worried about privacy in the robust stats setting.
Mm-hmm.
I mean, we could add it on top, but usually we are thinking about some different situation. We're worried about doing statistical inference when maybe some malicious adversary messed with 1% of my samples, some largish constant fraction of my samples, like 1%, 2%, not just one sample. And we still want to design interesting algorithms. Okay, so there was like 100 papers on algorithmic robust stats. People made a lot of progress on designing efficient algorithms for robust statistics. One of your, I believe your co-organizer, Gautam, is that true? Is Gautam is
Yep.
also
Yep.
a
Yep.
member
Yep.
of the organizational team? Yeah, that's what I
Of
thought.
course.
So in about 2020, Gautam reached out to me and said, "Hey, we should talk about whether we can use any of these robust statistics ideas for privacy." So Gautam had sort of scouted out this privacy stuff. He was also kind of trained as a theoretical. Gautam's a great bridge between machine learning and theory communities. Um, and he reached out to me and he said, actually, he said, I have this amazing master's student. We should work with him on figuring out the connection between robustness and privacy. And okay, it took us, there were a few false starts. It took us a while to get going, but eventually, actually, Gautam had done an amazing job of distilling some simple problems that we didn't know how to solve with the right privacy accuracy trade-offs, and that were just super appealing to a theorist. And so eventually I bit. And Gautam and I and his amazing master student at the time, Mahmoud Majid, who's now a PhD student at MIT, worked on this in 2021, 22, and got our first privacy result. And that was a theory result. So the theory results have all been published in theoretical venues.
Mm-hmm.
So what was the trajectory to trying to push these things a little bit more to practice? I guess I've felt for several years, I felt like there wasn't quite enough effort being spent in the theory community on this, especially the people who were doing this robust stat stuff, or the community that was doing this robust statistics stuff. I thought there were a lot of incredible new ideas in this
Mm-hmm.
algorithmic robust statistics literature. And I thought these have to be useful somewhere. Like, we shouldn't just all keep talking to each other in these theory conferences. Somebody needs to go like see if anybody wants this. And I don't, okay, to be clear, like, I don't think you should go around shoving your new theory ideas down people's throats, right? Like, that's a bad look. You shouldn't do that. You should go out and like try and listen and see if there's somebody who might need what you're doing, and see if you can build a bridge. And it seemed like the privacy thing was maybe such a bridge. So it turned out, I guess I didn't quite emphasize this. It turned out that a lot of the algorithmic ideas from this robustness literature had very natural translations into privacy.
Mm.
And so uh, but people actually care about deep differentially private algorithms in the real world. It's not clear they care about these robust algorithms in the real world. And so I thought, okay, I mean, I still think this, and I have no idea how successful this is going to be, by the way. Like, I've been going around saying this for a couple of years and everybody just politely smiles and nods their heads, but it's like, if it's good, okay, do we really believe that what we're doing is useful? Like, do we believe in the science? Because if we do, we should go try to use it. And if we
Yeah.
don't, then what are we doing?
Wow.
Something else.
Some hot takes being dropped. This is gonna be some hashtags happening
Yeah, fine.
for our podcast. No, that's a great perspective actually, and one that, I'm also trained as a theorist, and I'm also someone that has started trying to speak more to practice people. So yeah, I appreciate all the insights that you gave us about this, and I also appreciate that we shout out to Gautam, who's amazing, and I will also link him on the review of the podcast underneath.
Yeah. Let me make one more just to temper my remarks a little bit. I still do lots of like purely theory stuff for theory's sake, and I believe in curiosity-driven theory. I don't believe that you have to have a usefulness litmus test on every piece of theory you produce. But I believe that sometimes curiosity-driven theory produces potentially useful ideas, and I believe in being opportunistic about it. So when you see something that you think actually has a chance of being useful, and when you are one of a small number of people who like are an expert in it, then I think it's time to go see if it maybe can actually be made useful.
Yeah. No, that's another great piece of advice, I guess. Or like, thank you for sharing the way that you're thinking
Well,
about this, by the way. It's like
I don't know if
really
it's
informative.
good advice. It hasn't really worked out for me yet on the practice side, but
I would say that you're doing pretty well, buddy.
yeah, man, it took a lot of submissions to get this paper into iClear. I got to tell you, we had a lot of rejects.
Yeah,
But
that's how it goes.
yeah, that's how it goes.
Oh, and I guess, that's a good segue, now that you mentioned your rejections, to start going beyond, topics slightly beyond research. We're still going to stay within the, academic realm,
Sure.
broadly. So you are an MIT faculty member, and I know that you have a handful of students already that you've been working with. So what is your favorite part about working with students? And you
Oh, I
mentioned
thought you were going to ask me who my favorite student was.
you can also
Which
mention that,
no,
and
we don't play favorites.
that's a great answer. But yeah, I want to hear your favorite part about working with students, and also to connect with your rejections that you mentioned earlier about the iClear paper, which again, like, I'm not sure if you have a student on the paper or whatnot, but
I have an awesome student on the paper, actually. It's Ty Rubenstein. Let me plug him. He's amazing.
awesome. We're gonna link him as well in the information for the podcast. But yeah, like, how do you help them deal with rejections? Because now you are the senior person in the room, right? Like, you are taking a different point of view compared to what was your point of view when you were a PhD student, like
Yeah,
Adam.
yeah. That's a good question. I don't know. How do I help them deal with rejections? It's not clear I'm that good at it, but I do try. So I guess what's my approach? I'm lucky to have, I should say, I'm lucky to have students who I think are really amazingly resilient. I think that a lot of it has to do with them, and there's, a lot of emotional resilience comes within, and I can try to support you, but a lot of it is their responsibility. And I'm really grateful that I have students that are amazing at this. So first of all, I think whether I was there or not, I think they would handle their rejections well. But I do try. So what do? We try to figure out if there was a reason. Like, we try to figure out if we get some reviews that we don't like, or reviews that reject the paper, we try to figure out, okay, we go line by line through the review and we say, what was going on here? Was there a misunderstanding? Is there something that we can do to fix the misunderstanding? Do we just think this reviewer was an idiot? That, sometimes we try to not say that. We try to be nice, but sometimes it's like, man, this person just did not spend the effort that they should have. Like, I'm going to stand my ground. So we go back, we have lengthy conversations about every line of the review and try to figure out what's going on. Then we go figure out what changes we're going to make to a paper. So that this is rejections for a paper, but of course this applies to fellowships and stuff like this as well. And then we try to emphasize what's important. Keep perspective. So I guess in two senses. One is in the life sense. It's very easy to become very emotionally attached to your professional success. I'm guilty of this.
Yep.
But it helps to keep, I think it's nice to sometimes remind people that there are other aspects of their lives outside of professional success. And it's not my job to tell them other aspects of their life, but it's sometimes when people get a really nasty rejection, it's nice to say, look, you're going to have a nice life anyway. You know, regardless of whether this paper gets in or not, there are other things you can focus on, and it's okay to focus on those other things, especially if they bring you solace. So there's the sense of broader life perspective. There's also a sense of professional perspective. Like, I try to tell students that you will be judged on your best couple of results. What matters is, do you have, you know, at the end of your PhD, if you have one amazing paper and a couple of others, that's a fabulous success. If you have one good paper and a couple of others, that's still a success. And so a rejection here, a fellowship missed there, like, this is just totally in the noise at the end. And so I try to boil it down, you know, I try to boil it down to a really small number of things that they should focus on, right? There should, like, and rejections or acceptances on things that are not on that critical path, we just try to let them slide off. It just doesn't matter. Things that are on the critical path, that's a bigger deal. That's when we focus on it. That's when we say, okay, how can we do better next time? But you identify a relatively narrow critical path, and you're like, this is what we're going to spend 99% of our emotional and mental energy on. And that critical path is your main result for your PhD.
Yeah. I do like a lot this, like, the way that you're approaching this, you know, like both the professional perspective, which is the thing that you emphasized, you know, at the second part of your answer, but also the personal life perspective, which is something that we tend to forget. And I think that especially us as like junior faculty, we are sometimes guilty of forgetting that too, right? Like, I don't know, I don't want to speak about you, but
No,
I
absolutely.
certainly
All the
forget
time.
about
All the
that.
time. All the time. Yeah.
Yeah. So, this sounds like, how did you get, how did you get, when did you know that, you know, the academic life is what you want your life to look like? Was there a moment that you were like, aha, like, that's what I want to do? Like, I just want to spend my time thinking about rejections.
I don't want to spend my time thinking about rejections. That's definitely not what I want to do. No, it wasn't one moment. So, okay, it's a bit embarrassing, but it's a bit of a family business for me. I have my dad and an aunt that I'm very close with are both are chemists. One's a chemist, one's a biochemist. So I grew up around academia. So like, you know, like many aspects of careers, where you come from it wasn't under my control, right? But I got lucky in that regard. So there was an aspect of it to that. That was what I knew. I went to college, and the first thing I decided to major in was philosophy. And
oh wow, I didn't know about that.
Yeah. I'm 5 credits short of a philosophy major, I think. Maybe 10 credits, something like that. I'm like 1 or 2 classes short of a philosophy major.
What?
And when I told my dad, he said, kid, you have to do something like that's employable in addition to philosophy. Like you can be a philosophy major, it's fine, but like you have to take some useful classes. And I was a rule following kid, so I did. I took programming, and it took a while for these threads to sort of conjoin, but they sort of conjoined on theoretical computer science. So later in college, I thought, okay, I graduated in 2013. So this stuff is all happening around 2010, 2011. And those were good years in tech, right? 10 through about 2021. It's like mega growth. You know, people were getting great jobs graduating with bachelor's degrees. I went to University of Washington, which has a direct pipeline. So it's in Seattle, has a really direct pipeline into both Amazon and Microsoft. People were getting offers from Amazon, Microsoft, left and right, offers from Google, Facebook, blah, blah, blah. Those were really good years. So I knew around 2011 that I had a choice to make. And I went and I did 2 things. I did an REU, which research experience for undergraduates, which are these kind of summer camps that the NSF sponsors and amazing hardworking people at various universities run. now that I'm a faculty member, I understand what an insane amount of work running these things is, and I will never do it. But I'm so grateful that other people do it. So I went to one at Rutgers, and I was mentored by Eric Allender, who's a wonderful complexity theorist at Rutgers. So I did a summer of research in computer science to get a sense of what that was like. And then the following summer, I went to Google to do an internship to get a sense of what that was like. And at that point, I knew I had to decide, did I want to do a tech route or did I want to try to apply to grad school? And it was a 100% fun-based decision. It was like, which one of these was, like literally, I was like, which one of these was just more fun on a day-to-day basis for me? So I was very privileged to get to make that choice, right? Like I had the financial security from my family that I didn't need to go immediately make a bunch of money. It was okay for me to get paid $30,000 a year as a grad student instead of $100,000 a year, which was the starting tech salary at the time. So all of those things lined up to enable me to do that. And I had the privilege of deciding like, what is just going to be the most fun to wake up to. And it was like, grad school seems fun. And so I always had this philosophy in grad school of like, if it ever stops being fun, I'll bail. Like I'll just go to the tech industry. Like why I'm not going to do this if it's suffering.
Yeah.
And mostly it kept being fun. It kind of kept being fun.
Well, you're still here.
I'm still here. Yeah, it's mostly still fun. It got less fun from grad school is the funnest, but for me, not for everybody.
Yeah, I was about to ask you actually, how do you feel that your life has changed, from undergrad student to PhD student to a postdoc and now to a faculty member?
Grad school and postdoc are the best. So, okay, my life is very nice. I'm very lucky, and many aspects of academia that I enjoyed early on, I still enjoy. I still love doing research. I love hanging out with my students at a whiteboard for hours. Some people, there's different styles of what you do when you're a professor, right? Some people become a little bit more high level. They make high level suggestions. I do that on some projects. There's plenty of projects where I don't understand what's going on technically. That's fine. Actually, Chara and I were discussing that before. You and I were discussing that before the recording.
Guilty.
So that's fine. I'm guilty of that. But I still love, on some projects, when I can do it, I still love examining every inequality and finding the sign error. Oh, we added that wrong. We need to subtract that one. And I love it. I really love that. So I still get to do that with my students, and that's the best. And I got to do that when I was like that. That's the thread that keeps me going. How did my life change? As a PhD student, I had a lot of time. You don't realize it when you're a PhD student, but you have a lot of time.
Yep.
I spent a lot of time barking up the wrong tree. It was very, 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 very inefficient, right? You have to learn all these litmus tests for ideas, right? Like 90% of the ideas, 99% of the ideas that you or anybody else generates are stupid. Like they're obviously wrong. And you have to learn these litmus tests, right? You have to learn how to test whether an idea is stupid, and you have to learn to fail fast, right? So as a grad student, you don't know any of these litmus tests, and you spend days working on stupid ideas. It's okay. Everybody does it. I did it. Everyone does it. And eventually you go to your meeting with your advisor, and your advisor hopefully nicely, runs these litmus tests on your ideas and then tells you why they're stupid. Hopefully they tell it to you nicely. But then you learn the litmus tests, right? So you're very inefficient early on because you're working on bad ideas all the time, and you learn to be efficient with your time. So I used to spend a lot of time reading papers, a lot of time working on bad ideas, but also a lot of time like going to lunch with my other fellow PhD students. Every day we would walk from the computer science building over to the salad bar and get a salad and sit around for 2 hours outside and eat our salads and chat. And it was great. It was wonderful. I don't have time for that anymore, unfortunately. As a postdoc, so I was a postdoc at Berkeley. Postdoc is also great. I was lucky to have a postdoc with a lot of freedom. I think in computer science, a lot of postdocs have a lot of freedom. If you're in like biology, maybe you have a little less freedom. You're a little more constrained to a grant. But in CS, a lot of postdocs have a lot of freedom. And the nice thing about being a postdoc is you're finally an expert in something. You're probably an expert in like one thing. Maybe if you're lucky, you're an expert in two, and you can sort of get your own research program going. So postdoc for me was sort of best of both worlds. I had the freedom of a grad student. I had no responsibilities, no teaching, no grant writing, none of that. I had still a PI, advisor, actually two. I had Luca and Prasad, who, were watching out for me, like who would catch me if I fell, sort of, right? Like if something, a research thing, a non-research thing, whatever, if it goes really badly, I had some people who were trying to look out for me. I still have that to some extent. Of course, my institution looks out for me, but it's less immediate. But I also had amazing students at Berkeley that I got to work with, right? So I worked a lot with the students there, and I functioned as sort of a junior advisor to some extent. That was great fun. That was a ton of fun. I got all the good parts, which is working with students, and none of the drudgery.
I bet. Yeah,
like, so that was great.
Postdoc is a sweet time, isn't it?
It was awesome. Yeah. And the one stressful part is that it's a limited time engagement, and you need to have something to do afterwards. And so many postdocs at some point in their postdoc do 1 or 2 academic job searches, and that is stressful. There's no way around that. That's a pretty stressful thing. And then as a faculty member, I have to try and be more efficient. I'm still pretty inefficient, but I'm more efficient than I was as a PhD student. I do a lot more context switching. I'm not the only one who says this. I think everybody says this. And so I've found that I'm really bad at context switching. And so I try to actively minimize my context switches, which doesn't always work that well. But so what's life as a faculty member? Some stuff just gets added on top, basically, right? Like, you got to write some grants, you got to teach a course, and different people approach these things differently. Some people, I think what I tend to observe is that most people don't do everything at 100%. It's just not possible. So most people find, a small number of aspects of faculty life to lean into and do a really great job and invest a lot of time and effort. And then they figure out how to do the other ones in a time minimal, effort minimal way. And do they do them as well? No, they don't. They do them well enough, right? So for some people, it's teaching. For some people, it's grant writing. For some people, it's organizing workshops and service activities. There's a wide range of these things, and you can't do all of them to 100%. So, I'm not going to admit to you which ones I try to do well and which ones I don't. I'm not going to say it publicly. But I think everybody does some version of that to make it doable.
Yeah, that is really heartwarming, both for me as a junior faculty member, but I also feel that it's going to resonate a lot with folks that are at the later stages of their PhDs and about to go on the job market. I want to ask you, because you mentioned it specifically about context switching, what would be, if you had to give me your best advice for like context switching, or like your best trick, what would it be?
Don't try to context switch after 4 p.m.
Hell yeah.
Like, it just never works. There's no hope, because it's going to take me 3 hours to context switch, and then it's 7 o'clock and I'm hungry. There's just no way. No. The actual thing is if I haven't loaded what I'm going to do into context by about 9 a.m., I'm really, like, I said 4 p.m., but actually, like, in order to actually do something on that task, it's probably 9 a.m. Like today it was teaching. Like today I was going to teach. I had a lecture to give, and so I gave my lecture at 11 o'clock, went fine. And then I had blocked off this big block of time to try and like get caught up on a student's project. So it was actually time without meetings that I was just gonna like read some stuff that my student had sent me. And it worked okay, but I didn't actively do any research in that time. I spent all afternoon from like 1 to basically when we started this call. I guess there was one seminar in the middle, just trying to context switch. So I guess the point is like realizing that it's going to cost you and allocating time accordingly.
Yeah.
So I don't know if that's advice for how to do it, but just to like know that you have to absorb the cost. The other thing is ignore your students. That's another good one.
Wow. I may block that off in the processing. But yes, please continue explaining to me.
No. Look. I am lucky to have absolutely fabulous students, and mostly my advice to them is useless anyway. And it turns out that if I just don't provide them with any advice, they go do awesome stuff, and then they come back and show me. And joking aside, you don't have to micromanage every project. And so the notion of like, if I try to context switch into every project fully, like learn every technical thing in every project, I'm useless. It doesn't work. And so I just have to say to some students, and I try to be upfront. I don't try to like be secretive about it. I try to say like, look, this is how I'm going to be in this project. I'm not going to have it paged in. You can ask me high level things. I will try to give you high level answers, but you're on your own for X. And I trust you to do a good job of it. I think you're going to do a great job. And typically they do. Right. So I don't literally mean ignore. I don't want to hide from them, but yeah, you have to delegate some stuff so that you don't have to have the whole thing loaded in your head at once.
I also find that in this topic of conversation, exactly, like I find that one of the pitfalls that we as junior faculty fall into is that because we are fresh off our PhD, where we are, as you said, the experts in, you know, one thing, it's like really hard to just give away this like control, right? Like you're like,
Yes.
oh, I
Yes.
know that. I can just like
Yes.
do it myself. I can just like I know I can
Yes.
see it, but that's not this is a disservice to you, and this is a disservice to your students who you're trying to train and teach them things.
Yeah. I think you have to, I mean, for me, I think you have to be able to turn it on and off or try to, the control freak aspect. Like when I was a senior PhD student or especially a postdoc, you know, I was writing a small number of papers and I was in control of every aspect of them. And every line of that paper was the best I could possibly make it be. And I love doing that, right? I love producing the very best thing I possibly can according to my metric of best. But that's not what it is to be a teacher,
Yeah.
right? That's so, you know, you try to turn it on and off, right? Like for some papers, for some parts of the paper, for some project, I'll be like, okay, this one I'm gonna go after. Like this one, I am gonna freaking iterate with this student back and forth. We're gonna go back and forth 20 times until this thing is the way I want it to be, and I'm going to explain every step of why I want it this way. Occasionally, I will do that if I really, really, really care. But also, I have to be like sometimes, you know, hey,
Yeah.
second year PhD student who's really awesome, you are writing these 10 pages, and I hope it goes well.
Yeah. Wow, that rings so true.
And I think the students find it arbitrary and capricious, you know, because it's very inconsistent. And they don't know when it's going to be like Sam in control freak mode, red ink, versus Sam in like go away and do whatever you want mode. But
Yeah.
they seem to be living with it okay, I think. I'm sure they're going to watch this and be like, what is he talking about?
Yeah, I will have a feedback form for students afterwards, Sam
Yeah,
students, if they
great.
want like a session to chat about Sam. Okay, well, I won't keep you too much longer, but before we close, I really, really want to talk about a very important topic, which is also mentioned on your website, which is
Hmm.
bikes
Mm,
and more generally work-life balance. Like,
yeah.
what do you do for fun? Do you have any work-life balance? I assume you do because bikes.
Yeah.
But yeah, talk to me a bit about this.
So I try to have work-life balance. I think I do okay at it, actually. Oh, well, okay. Do I do okay? I don't know. It's hard to assess your own work-life balance, but uh, yeah. So I love outdoor sports activities. My big one is riding road bikes, but I also like cross-country skiing. Occasionally, I'm a runner, although I don't like running that much. It's just like a thing I do. It helps, you know, feel happy. Um, I swim, this kind of stuff. So I like this stuff a lot. Um, and I've liked it since I was a kid. You know, my again, I got this from my dad. My dad used to take me on road bike rides since I was, you know, 9 years old or something,
Oh, wow.
and it really stuck with me. So I'm I'm just I don't know. I don't have anything like super earth-shattering to say about it, but yeah, I'm pretty ruthless about making sure that bike rides happen. It depends on the season,
Oh, that's
but in biking season, surely once a week. In the summer, it would maybe twice a week, usually, maybe even a bit more parts of the summer. Um, but and then there are other workouts that are like not on bike days because in
mm,
Boston you kind of need to drive out of town a little bit to go biking in a nice way. So it takes a little bit of time. But
yeah.
you know, and I also I am fully willing to leverage the flexibility, the hours flexibility that we are afforded in our job when I need to. So it's not uncommon that I will clear a weekday and use it to go do something that's not work. Like
Yeah.
I work enough weekend days that, you know, I don't feel the least bit bad about canceling all my meetings on a random Tuesday
Amazing.
and going biking. So I do that. Yeah, probably every couple weeks. That'll happen.
I really love that, we said this out loud. I mean, I don't really love that, you're working on the weekends, but
Oh, come
you
on.
know,
All of us work on the weekends.
you know how it goes.
Yeah.
And I will put you on the spot here before we close.
Yeah.
You volunteered earlier to show me your dog.
But yeah, so he's
Is he
actually
still here?
here. Yeah, he is. And I gotta tell you, I think the Zoom noise cancellation is pretty amazing because he has been barking this whole
Oh, oh
time.
my
But here he is. Here's my dog.
God.
He's a 28-pound Australian Shepherd, and he's a COVID puppy. So he's
Oh, he's
about 4 years
so
old.
cute. I mean, I obviously know Avi,
Yeah,
but yeah, he's famous.
he's internet famous. Yeah, there he is. Mwah. Okay, back
Hi,
to on, bud.
Avi. Okay, well, Sam, our time is almost up here.
Hmm.
Thank you so much for a wonderful conversation. And thank you to all of our listeners for spending your time with us this evening or whenever you listen to this podcast. And don't forget, if you enjoyed this podcast, please smash that subscribe button. Okay? Thanks, Sam. See you all
Thank
next
you all.
time.
Thank you, Chara.